so happy to be here. 5 years ago, I was invited as a backup speaker, ready to step in if somebody had a problem. Luckily for everyone, my intervention was not required. But here we are now, 5 years later, and I'm, again, so happy to be here, to stand in front of you with a talk that you can say has been a long time coming. I would like to start by thanking Arne for his trust, and I would like to thank Raf for his support and feedback in the preparation of this talk. Okay, so this talk is an investigation into the theoretical foundation of Lisp, the formal mathematical language. This is not a talk about McCarthy implementation of Lisp or any other Lisp system. We will go back in time and shed light on various episodes in the history of mathematical logic in order to understand what it is that McCarthy did precisely. These various episodes structure the present talk, and by the end of it, hopefully, we will understand both Lisp's origin story and the confusion around it, in particular with regards to the Lambda calculus. Okay, in 1928, David Hilbert gave a talk at the International Congress of Mathematicians in Bologna. His talk was titled Problems of the Grounding of Mathematics. Concerns about the foundation of mathematics were prevalent with the discovery of paradoxes. There was one type of self-referential paradox in particular that kept creeping up in various places. In set theory, it is known as Russell's paradox. Here's a quick recap. Some sets are members of themselves and others are not. For example, the set of all sets is a member of itself because it is a set, while the set of all penguins is not because it is not a penguin. Now consider the set of all sets that are not members of themselves. Is it a member of itself or is it not? If it is a member of itself, then it is not. If it is, then it is. If it is not, then it is. Contradiction. So that paradox appeared in naive set theory, and it also appeared in Gottlob Frege's attempt to ground arithmetic in logic. However, the important idea for Russell was precisely this, the grounding of mathematics in logic. So when he and Whitehead wrote their treatise on the foundation of mathematics, the multi-volume Principia Mathematica, they made sure the paradox wouldn't come and bite them. Now, contrary to logicists like Frege and Russell, David Hilbert was a formalist. The formalists were less concerned with the axioms themselves as with the consistency of the theories those axioms were underpinning. They saw mathematics as syntactic forms that take shape when given a semantic interpretation. They were treating mathematics as a game of symbols, if you will. Now, David Hilbert had successfully demonstrated that geometry could be rigorously formalized. And now, in Bologna, he rallied the mathematical community around his grand plan to formalize all of mathematics. And this moment in history of mathematics is known as Hilbert's program. Hilbert's program goes something like this. Starting with an axiomatized theory and a proof system, say set theory and first order logic, establish the following. One, show that the system is complete, that all statements in the system can be proved or disproved. Show that the system is consistent, that it doesn't allow for contradictory statement. 3, come up with an effective method for deciding if a statement has a proof. And this is a decision problem. And it is known as the Entscheidungsproblem. In the audience of Hilbert's talk was Kurt Gödel, a 20-year-old Austrian mathematician. Now, this prodigy published 3 years later his incompleteness theorems, showing the limits of the formalist approach. The first incompleteness theorem says, and we'll go fast here, that in a consistent formal system, there are statements which can neither be proved nor disproved. The second incompleteness theorem states that a formal system cannot prove that it is consistent from within the system itself. As for the decision problem, Alonzo Church and Alan Turing would demonstrate separately that the decision problem cannot be generally satisfied. In other words, there is no mechanical method that can tell us if a statement has a proof or not. Okay, so this is a little bit, yeah. Okay. So in a narrow sense, Hilbert's program was dead in the water. But Gödel's work opened the door to proof theory and validated the questions posed by Hilbert, replacing absolute certainty with partially secure and reliable foundation of mathematical knowledge. Gödel was able to create a statement within Principia Mathematica that said, I am not provable. Now recall that Principia Mathematica was a system designed from the ground up to prevent self-referential statements of the sort. So that was quite the plot twist. At the heart of the proof was the arithmetization of syntax, assigning unique numbers to syntactic elements, an operation called Gödel numbering. Principia Mathematica was the axiomatic theory Gödel had targeted, but his results were general, valid for any formal system strong enough, and here's the precise part that we didn't said earlier, any formal system strong enough to define the primitive recursive functions. And in textbooks, you will often see a formal system enough that has piano axioms or that has the expressive power to do arithmetic or to carry arithmetic calculations in it. So now we're going to see the very precise reason that the requirement is a formal system strong enough to define the primitive recursive functions. So those are the functions that were used on Gödel numbers to construct a self-referential statement. Okay. So it was very clever proof, a mathematician's delight, and people were talking and trying to understand it everywhere in the world, but in particular in Hungary, mathematicians maybe there were the first to measure the significance of Gödel's results. John von Neumann, for example, was in the audience when Gödel announced his results at a conference in Königsberg in 1930, even before publication. And there were his peers, Laszlo Kalmár and Rósza Péter, quickly followed in interpreting and disseminating Gödel's proof. And it is she, Rósza Péter, who realized that Gödel's recursive functions were important in their own right, not just as a tool for proving incompleteness. This insight led her to publish a paper advocating the study of recursive functions as a field unto itself. She presented that paper at the International Congress of Mathematicians in Zurich in 1932, and then she then proceeded to write the first papers in that field. It was also Rósza Péter who coined the term primitive recursive functions to differentiate them with other recursive functions. And she presented another paper on recursive functions at the International Congress of Mathematicians in Oslo in 1936. She was forbidden to teach by the fascist laws of 1938, of 1939 actually, but she resumed her career at the end of World War II, straddling recursion theory, computer science, and pedagogy in mathematics. Now, it's true that the names most often associated with recursion theory are Kurt Gödel, Stephen Kleine, Alonzo Church, Emil Post, but according to Kleine himself, and I quote, Rósza Péter was the leading contributor to the special theory of recursive functions. Now let's look at recursion theory proper. Recall that Hilbert posed the Entscheidungsproblem, a decision problem, asking if there is an effective method or an algorithm that can give us a yes or no answer as to whether a theorem in a formal system has a proof. The question then becomes, what exactly constitutes an effective method or an algorithm? And that's how the quest for formal models of computation began. In recursion theory, one of these formalizations, we formalize an ideal version of computation by providing a set of definitions, mathematical definitions, describing a class of computable functions. And the idea is to start from the simplest functions possible and build upwards, preserving the property of computability as we go. And you might recognize the piano, the same functions as in the piano axioms, and that's why they are both brought up when we talk about what you need in a formal system for it to comply with Gödel's requirements for them to be incomplete. So a set of definitions include basic functions and the operations you do on them, you apply on them, on those functions. And for the primitive recursive functions, these are the basic functions. So first, we have the constant zero function, and in Clojure, we're going to translate that to constantly zero, a function that receives any argument and outputs a zero. That is intuitively computable. That's something that we want. The successor function is the function that maps n to n plus 1, and that's also something we want in our definitions. And then the projection functions is a bit more technical, but it's an identity function, higher arity. And I'll get back to that later. So with the operations of composition and recursion, we build new computable functions. For example, if you want to add 2 and 3, we can call the successor function 2 times on the number 3 or 3 times on the number 2. And it's this projection function that allows us to select whichever argument we want to recurse over. Now, what is so neat about, by the way, these comp and recur are very, very rough approximations. This is just to give you an idea, but it's not how, the machinery is a bit specific, but it's really the same idea. So what is so neat about the primitive recursive functions is that this small set of definitions is sufficient to cover all of the familiar operations on the natural numbers. Addition, subtraction, multiplication, division, modulo, return, the nth prime, exponentiation, factorial, all these are primitive, can be defined in these primitive recursive functions. Nothing else but these primitive functions closed over, as the mathematicians like to say, by the operations of composition and recursion. But you don't have all, if you have all this, you can also, as Kurt Gödel did in his proof, you can also say, well, 0 is false and all the positive numbers mean true, and then you have the propositional calculus inside the primitive recursive functions. And then you can start doing fancy stuff. So, for example, you have the Boolean function which say, okay, instead of 0 and all the positive, I'm going to normalize, and I say 0 is false, and any other positive number means 1. So I have kind of a normalization function. Negation is exactly the opposite, and then conjunction and disjunctions are clever ways to look at addition and multiplication, knowing how they work with the 0, and then you have and or, and you can also then have the conditional, and you can program in the primitive recursive function. We're going to go back to that later. So the first example of a recursive function, which is not primitive recursive, was discovered by, or proposed by Ackermann, a student of Hilbert. And he might not have been the first because there's another student called Gabriel Soudan who also proposed a function which was not primitive recursive. And these are functions, I think I have any, yes, these are functions that are constructed by nested recursion on multiple arguments simultaneously. Something not reducible to primitive recursion. And the Ackermann function grows much faster than the class of primitive recursive functions. It is Rósza Péter who standardized this version of Ackermann function that we know from most textbooks and on the Rosetta Code website, because the original form had 3 arguments. Okay, so I actually need to go back to the previous slide because I want to ask a question. So we've seen the primitive recursive functions, right? Then we know, I already said there are also functions which are not primitive recursive. But the general question is this. When you have definitions of a certain class of functions, how do we know if our definitions capture the class of the computable functions? And the answer is that we never know that. So our definitions are always a working hypothesis for the computable functions. And they hold until a computable function is discovered outside the class that our current definition describes. And as the field of recursion theory matured, 3 classes of computable functions were discovered, each bigger than the previous one. So David Hilbert and Gödel were working with the primitive recursive functions, and then Ackermann, Soudan found a function which is not recursive, which falls in the class of total recursive functions, because both the primitive recursive functions and that Ackermann functions are defined on all their inputs. And then we have the partial recursive functions which are not defined on all their inputs. So if you remember how the definitions for the primitive recursive functions look like, you can see that it's the same set of definitions except for the minimization operator, which has been added here in red. And this is adding this operator, the minimization operator, which is an unbounded search operator, makes this class the partial recursive functions. Now, intuitively, primitive recursion corresponds to a bounded search space where we know in advance how far we must search for an answer. Partial recursion corresponds to an unbounded search space when we don't know in advance how far we must search for an answer. Think, in programming language terminology, a for loop versus a while loop. Douglas Hofstadter illustrated this in Gödel Escherbach, his book on all kinds of interesting stuff, very much inspired by Gödel's work. He devised two toy programming languages, bloop and floop, bounded loop and free loop. And they correspond to primitive recursion and partial recursion, respectively. Now recall the question we asked earlier, and let us ask it again. How do we know if the class of partial recursive functions capture all of the computable functions? And the answer is, again, we don't. Nothing changed. Fundamentally, we just discovered a class of a set of definitions that can describe more functions. But here's the thing. It has been shown that the class of partial recursive functions coincide with the functions that can be computed by Turing machines. And the significance of Turing machines is that Turing's formalization of computability is authoritative. Gödel himself said the correct definition of mechanical computability was established beyond any doubt by Turing. Now, Turing modeled computability on how a human would perform calculations step by step, capturing the notion very intuitively, and much more intuitively than all the others who proposed theories of computation which are more algebraic or all kinds of stuff. For example, Church characterized computability in terms of Lambda definability. Emil Post characterized it in terms of finite combinatory processes. The partial recursive functions have been actually put together by Kleine, Herbrand, who died very early, and Gödel. So they are sometimes known as the Kleine, Herbrand, Gödel functions. And all these models of computation came together more in 1936. So this year is kind of magical for computability. And all these models of computation have been shown to be equivalent. But the belief that they describe and exhaust the notion of computability is a belief, and it is known as the Church-Turing thesis, and it is disputed sometimes. Okay, we now have all the pieces to understand what McCarthy did with Lisp. Recall that McCarthy was interested in AI. He wanted to encode common knowledge and reason computationally on that domain. And that idea is actually very old. It's something that goes back at least to Leibniz in the 17th century, and we can find other people who had similar thinking. Different cultures, different paradigms. But McCarthy, he knew how to go about it, and the list structure was the key. And that's an idea he got from IPL, the information processing language. McCarthy realized that this list structure could be used for data, but also for code, as he could model function definitions in it and label them. He formalized this list structure as S expressions. He then proceeded to take the definitions of the partial recursive functions, but instead of functions on numbers, he defined them as functions whose domain is S expressions. And instead of the traditional recursion and minimization operators, he introduced recursive function definitions and the conditional expression. Not only was this working, but it was neat, and mathematical elegance was always a goal for McCarthy. In summary, Lisp was devised as a programming language, but in the process was simplified to define a formalism, and I quote, as a vehicle for developing a theory of computation. This is why I like to say that John McCarthy invented Lisp twice. He led the development of a programming language as an object in the real world, and he devised a formalism in mathematical logic, an idea, a representation not tied to any implementation. Had he invented Lisp only once, whether as an object or as an idea, he probably would have been celebrated all the same. Both inventions were exciting, groundbreaking, influential. And today, 65 years odd years later, the Lisp as object, the Lisp as implementation is all but forgotten. You need forgotten hardware or non-existent, dead hardware or emulation of that old hardware to run this original Lisp implementation. On the other hand, Lisp as an idea, the McCarthy formalism thrives. It is found behind every Lisp implementation that came after McCarthy's. Now, to the question everybody wants to know, what about this tendency to associate Lisp with the Lambda calculus? Well, why don't we turn to John McCarthy and listen to what he had to say on the topic. To use functions as arguments, one needs a notation for functions, and it seemed natural to use the Lambda notation of Church. I didn't understand the rest of his book, so I wasn't tempted to try to implement his more general mechanism for defining functions. Yeah, it is kind of funny. Now, having borrowed this notation, one of the myths concerning Lisp that people think up or invent for themselves becomes apparent. and that is that Lisp is somehow a realization of the Lambda calculus, or that was the intention. Oh, okay. Okay, so if we I want to add something on this confusion with the Lambda calculus. Something else that could explain the confusion around Lisp and the Lambda calculus is the series of papers that Steele and Sussman published in the 70s when they bridged the gap between programming language semantics and models of computation used by theoreticians, particularly the actor model and the Lambda calculus. Out of these experiments came Scheme, the first Lisp system with lexical scope. But now, if we ask the question about why Lisp and the Lambda calculus are being associated, what about the Turing's formalism? How did that inform McCarthy and when he developed Lisp? So again, I want to listen to what the man himself has to say. So in the early days of computing, some people developed programming languages based on Turing machines. Perhaps it seemed more scientific. Anyway, I decided to write a paper describing Lisp both as a programming language and as a formalism for doing recursive function theory. At the same time, I want to add that the notion of a universal function came from Turing. Another way to show, and I quote now McCarthy, another way to show that Lisp was neater than Turing machines was to write a universal Lisp function and show that it is briefer and more comprehensible than the description of a universal Turing machine. This was the Lisp function eval. And finally, Russell Péter, somebody on McCarthy's team, noticed that eval could serve as an interpreter for Lisp, promptly hand-coded it, and we now had a programming language with an interpreter. And the rest, as they say, is history. In conclusion, I hope we have established the origin of Lisp and cleared up some misconceptions around it. I would like to argue that mythology is a constant trait of the scientific narrative, and to support this, I'm going to briefly enumerate other misconceptions or myths that we hinted at in this present talk. So one is Gabriel Soudan being left out when talking about the first example of a recursive function that is not primitive recursive to the benefit of Ackermann. Another misconception might be that Turing is often represented as resting on Gödel's shoulders, while evidence suggests, at least according to some research, that he was working from first principles and that it was a completely independent endeavor. And finally, Rósza Péter doesn't get the recognition she deserves as the founder of the field of recursion theory. So the broader question of representation, scientific myth, and what we like to tell ourselves or why is beyond the scope of this talk. But before leaving, I would like to entertain you with the idea of using Lisp as an exposition method for the primitive recursive function. So above, the first half of the slide shows you the traditional mathematical notation that you will find in textbooks, on Wikipedia, encyclopedias, and stuff like that. The beauty, of course, of Lisp is that it's symbolic computation. We can model anything, including mathematical frameworks. So we can indeed translate the formulas into code, and then we have a program we can run. And then we have a REPL to examine things interactively. And you had a glimpse of how this works on the slide with the closure code translating the basic functions of the primitive recursive functions. But the whole thing, the whole machinery is more involved, but I've explained the gory details in a post that you can find on my blog. It is called Lisp's grandfather paradox, because we are time traveling back to Lisp's progenitor, if you will. Now, can you guess what the code on this slide is doing? You can ask me to see if you want to see dependencies of this function. You can ask me. I will show you. But let's hear it from the audience. If anybody can tell me what this is doing. And there is a pretty serious hint there. It's a tribute to McCarthy.
It's making my head explode.
Okay, believe it or not, is the if then else function. That's it. And I'm done. Thank you very much.